thank you, Alina and Michael, for the opportunity to talk in this seminar today. Yeah, talking about additive properties of convex sets, and the works I'm discussing is work in progress, joint work with Tom Bloom and Jakob Führer. So this is a number theory seminar, and I guess this talk is not really a number theory talk, more of a combinatorics talk, really. But there is at least a small link to number theory, which I'll try to explain as we go. So let's talk about what a convex set is. You probably have an idea of what a convex set is, and it's probably not this. So usually when people think about convex sets in maths, we're thinking about some sets in space where you can draw a line through any 2 points and you stay inside of the object. And that's not what I'm talking about. So for me, a convex set is a finite set of real numbers with this property that its consecutive differences are strictly increasing. So here's this described in a more mathematical way. So that we write the elements of A, we label them now in increasing order, A1 through to AN. So this says that, yeah, the difference between these two elements, AI and AI minus 1, is strictly less than the next consecutive difference. And that holds for all I such that this expression makes sense. So that's all I in this range. I don't know if you can see when I'm pointing at these things with my cursor. Yeah, okay, great. Okay, so the way I think about this is that this set kind of it's sort of spacing out more and more over time. Maybe another way to think about it that might be helpful is to think of this more analytically than combinatorially. Then it's to say that a set is convex if it's the image of the first n integers under some strictly convex and increasing function. So both of these definitions are the same thing said in a different way. These two definitions of this object are equivalent. So here's a picture of a convex set. This is I guess a very number theoretic example, which is the squares. F of x equals x squared is the function, and on the x-axis here we have the integers from 1 to 5, and on the obviously we have the curve y equals x squared, and then we look over here for the convex set. So the convex set is where these dotted lines meet the y-axis, and we can see here that the gaps are strictly increasing as we move up the curve. Okay, and yeah, the set of the first n squares. This is a real classic object in number theory, and some of the questions that you can ask about this are how many distinct sums do the first n squares generate? How many solutions do you have to certain additive equations in the squares? And things like can you have what sort of properties of arithmetic progressions can the squares have? So these kinds of questions, and these are the kinds of questions I'll be talking about today, really just, I suppose, replacing the squares with this more general convex function. But with a more general convex function, we don't really have number theory to call on. We don't really know anything like number theoretic when the convex function is so general. It's really hard to get to grip on it. F of x equals x squared is rather special, and already these questions are quite hard for this very specific function. So we're making them much more general and much harder. And I guess this is part of the field of sum product theory, where we take these hard questions from number theory and generalize them to make even harder questions that we really can't answer. So maybe I won't really talk about the sum product problem today, but this is this convex set often coming in the context of the sum product problem. So if you know what that is, then there's a helpful link, and if you don't, then I guess you can safely forget about it for the rest of the time. Okay, so that's the definition, and I've got this sentence here: convex functions destroy additive structure. Let me explain what I mean by that. So we've got here this very additively structured set along the x-axis, the integers from 1 through to n. It's very structured. It's defined by addition. You get from one step to the next by adding one, like additive rule. There's loads of patterns that are additive in there. There's lots of there's obviously lots of additive patterns, and I suppose there are different ways to kind of quantify what it means. But I guess we could all agree that this set is about as additively structured as any set could possibly be. And then we hit it with this function f, this convex function f, and we look at what happens now on the y-axis. And it seems like the additive structure gets kind of messed up by this f. Now the gaps are increasing strictly, and we sort of thinking that, well, we probably intuitively we should kind of destroy these additive patterns that were there in the first place. And how precise this statement in blue really is depends on how you quantify what additive structure is, how you define your additive structure, the different interpretations of what additive structure exactly is. So let's talk about what additive structure could be. So the first measure I would suggest is the size of the sum set. So sum set, this is probably a definition many people here are very familiar with. So this is sort of the key object in the field of additive combinatorics, which is my main area of research. So we start off with sum set A, with a set A. Again, a set of reals. By the way, all of the sets I talk about in this talk from now on are going to be finite sets of real numbers. And I just might forget to say that sometimes. So that's a disclaimer. So A here is some finite sets of real numbers. And the sum set is defined by taking all just of the pairwise sums. So we have some idea how big could this be. The trivial range, A plus A is always at least as big as A. And it's at most as large as A squared. And if we're close to the bottom of that, if it's small, if it's linear, that suggests that there must be some good reason for that. Something special must be happening, and that special thing should be additive structure. So Erdős conjectured that for a convex set, this sum set is essentially as large as possible. So A plus A, always bigger than A to the 2 minus epsilon, but this should hold for all epsilon greater than 0. And for, I suppose here for A, sufficiently large with respect to the constant epsilon. So roughly speaking, the conjecture, the expectation is that for a convex set, the additive structure is so messed up by the convex function f that the only possible option is that the sum set's very large, maximally large, up to a small loss. And actually, it's the squares that show us that we can't remove this epsilon entirely. Because for the squares, the sum set has size a squared divided by a square root of a log of the size of a. And this is, I guess, a number theory that's about 1 century old now. So yeah, this convexity, this Erdős conjecture is still wide open. So the answer for the squares is well known, but for a general convex set where we don't have that number theoretic structure, we don't even know that these things are integers. So we can't use prime decomposition or anything like that. This problem is open. There's been a lot of work on this area by a lot of very smart people. I think some of them may even be in the audience. So I won't name all the names because there's quite a lot to name. But perhaps some of the key players here. So there was a bound A plus A bigger than 8, A with exponent 5 over 2 here, which came from a few different sources. Sorry, 3 over 2. I meant to say 3 over 2, which came from a couple of different places. There was an incidence geometric proof from Erdős, Nathanson, and Rouge, which is very nice. There was also some more elementary arguments. There was a proof of Garayev, and there was a paper of Konyagin. Shkredov and co-authors have worked on improving this, including a very nice paper of Shen Shkredov. The current record is this result of Rudnev and Stevens, which I think is about 4 years old now. The exponent's 30 over 19, and we think it should be 2. 30 over 19, maybe the key thing to emphasize here is that this number is bigger than 3 over 2. 3 over 2 you can get quite easily now. I mean, at least in retrospect. And this they had to work a bit harder for. Okay, but yeah, the exponents aren't so important really for us right now. The point is that this is a problem. We know something, but it's still open. We have quite good bounds, but we have a lot of space to improve still. A second measure. There's different ways we can quantify, and another one that's probably the second most common method for these things is the energy of a set, which I've already kind of alluded to. So the energy of a set counts the number of solutions of a particularly important additive equation. So additive energy, we call it. Let's define this thing. So given this set A, and A is just an arbitrary set of reals, the definition is that E of A, the energy of A, counts the number of solutions to this simple symmetric additive equation, A plus B equals C plus D, with the variables all coming from the set A. Okay, so yeah, we can think, roughly speaking, that if A has this additive structure, these kind of additive patterns happening, then we should get many solutions to this equation and the energy should be large. And the range here, the trivial range, now the energy is always at least A squared, the size of A squared, because we have trivial solutions, A plus B equals A plus B. These are always solutions. And the upper bound is that this quantity is at most the size of A cubed. That's just because 3 variables fix the 4th one. And so where in this range could we be for convex functions? That's a reasonable question. And there's this sort of, I don't even think I can really call it a conjecture because I've not seen anybody like really strongly tell me that they think this is true. But there's a sort of speculation in this area that this bound, this optimal bound is, so basically the energy should be almost as small as possible. You can think of this, it's a bit like this conjecture from Erdős on the previous slide. The subset should be as large as possible. If we knew this energy conjecture, we would also get the Erdős conjecture. I actually suspect that this may be false, but I haven't been able to prove it. What I will be talking about today is some constructions which we came up with partly in an attempt to show that this conjecture is false, where we could find some surprising structure in a convex set. Oh yeah, and what's known for this, the current bound is quite a recent improvement from Tom Bloom. And I guess the key thing again to mention here is that this is a bit better than the kind of threshold, which would be exponent 2.5 here. What's the truth of this question? I think that would be really nice to answer that. I don't know. I feel like we're going to get there eventually. Like someone's going to find a counterexample to this conjecture, I think, and it might happen in the next months or years, or maybe we have to wait a bit longer. That's my guess. But again, just speculation. So these are like the classic measures, I guess, of the classic kind of problems for convex sets. And in this joint work, we considered a different measure, which also feels like a very natural one to consider, which is counting 3-term arithmetic progressions. And that's the one I'm mostly going to be talking about today. So here's the definition. This T of A is counting here all of the solutions to this equation, A plus B equals 2C. It's a bit similar to the equation from the previous slide, except that one of the variables is repeating. So it was the D equals C case of the previous slide. And this, you can think of this as just an equation, and a simple linear equation which should encode additive structure, but this has another meaning particularly, which is that it encodes 3-term arithmetic progressions. So what we're asking about here is how many 3APs can the set A have? And again, here's some context here, some trivial bounds. So the upper bound T of A is always less than A squared. This is for any A. This is just, again, because two variables determine the third one. The lower bound is again coming from the trivial progressions. These are the progressions A. So the progressions with common difference 0. They don't really sound like three-term arithmetic progressions, but they all are according to this definition. So we're somewhere in this range. And with this additive structure, with this assumption of convexity, which appears to be a not additive structure condition, we might expect that this upper bound we should be able to do better than this upper bound. So can we do better under the assumption that A is convex? This is the question that mostly focusing on in this joint work and in this talk today. Of course, I should just say that if anyone wants to ask questions at any time, go ahead and interrupt me. I'm happy to answer them. I'd like to answer them. It's always nice to know that people are listening in Zoom talks when it can feel a bit spooky sometimes. So, yeah, and this is just, I thought I should get some more pictures in here. Here's a picture of a three-term arithmetic progression. And you know what three-term arithmetic progressions are, but here's some colors. Here's another one, and here's another one. Okay. There will be, I've been spending a lot of time trying to make pictures for this talk. And this was like almost the limit of my tics ability. All right, so let's first of all just slightly improve on this trivial upper bound. So there's an observation in our paper, and I think this is kind of just really a starting point. I wouldn't really call this a theorem, which is the observation is just that we can improve this exponent of 2 down to 5/3, kind of, without really trying too hard. So here's the short proof. I think the one proper proof of this talk. So we define this thing R of A plus A of X. This is counting the number of representations of X as a sum in A plus A. So how many ways can we write X as a sum? This counts. And we just note that this TA can be expressed as a sum of this representation function. So RA plus A of X summed over all X in 2A. 2A just means the dilate of A by 2. This is exactly the same thing as TA, as we defined it on the previous slide. So then we just notice, there's this theorem of Schön, which has also been proved a few other ways now. So there's a few interesting proofs of this bound. So Schön proved this bound RA plus the number of representations at X is small for any convex set. Actually, you could think of this as another measure of additive structure. How many ways can a single element be written? This Schön result is optimal. And that's actually one of the things we're going to be explaining more when we do finish writing this paper. So we have this upper bound for this RA plus A. And if we just plug this in here and do the rest, the 5/3 falls out. So we get 5/3 as a starting point for this question. A non-trivial bound exists. We also know, a couple of other ways to get there. So we don't know how to improve this actually at the moment, but well, we have an idea that we hope we can make work. So what I'm mostly going to be talking about actually is the other side of this problem, which is showing that there's a convex set with this number of 3APs quite large. So constructing a convex set with many 3APs, and yeah, the main result is that we have this, we can construct a convex set with a sort of surprisingly large T of A. And this is this joint work with Bloom and Führer. There exists a convex set A with the property that this number of 3APs is at least the size of A to the 3/2. So like quite a bit better than the trivial bound of size A. Okay, so that's the main result, which I'll sort of spend a fair chunk of time during the rest of this talk trying to explain. So just doing a time check. And yeah, maybe this statement is a bit casual, because we could just take the convex set to be, say, have two elements. I haven't also explained what this notation means here. In a number theory audience, I guess people see this all the time, so I won't labor it too much. But actually, a student recently asked me to write down a proper definition of this notation, and I realized it's kind of it's harder than you think. It's sort of like tripped me up a bit, actually. We all know what it means, but it's actually quite hard to formally express, I think. Anyway, so this means that there's an absolute constant. So this is true. For this to be interesting, it needs to be true many times. So what we're saying is that there is some constant C, which is positive. Actually, I forgot to say that's a positive absolute constant C, such that we can find convex sets with this large number of 3 APs for all sufficiently large sizes. So actually what we prove in the paper to get to this theorem up here is this other theorem down here. And this is really our construction, and it gives a little bit more information. So that the second theorem here implies the first one up here very quickly. So there exists a convex set with many long arithmetic progressions. So it has about root A many arithmetic progressions of length about root A. And once you know this, you quickly get this earlier theorem, because inside each of these progressions of size root A, you have about A many arithmetic progressions. And then you sum over all of the, A many 3 APs in here, 3 AP, 3 term arithmetic progression. And then you sum over the root A many, and you get this A to the 3 over 2 up here. So really, this is the thing we need to prove. So yes, this is a set, and it has some kind of, it's a convex set, but there is some additive structure in it because it's got many 3 APs, and it's also got sort of many long arithmetic progressions. So it feels like this earlier claim that I said, the convex functions destroy additive structure. Well, that's not really true here, because this convex function has left some of the additive structure behind. This A here still has some additive structure, not like as much as a real progression, as a true progression. But destroy feels like a strong word, so I suggest you could change it to something like disturb or disrupt. Okay. So there is a very nice paper of Ruja and Jalozov from 2019, which was quite sort of a key influence for us. And I think it's a paper which not that many people maybe know about. It's a 3-page paper, and they construct also a convex set with some additive structure. This is their theorem, which maybe it's not obvious how this is related to the main question, but let's take a moment to try and understand what their theorem says. So there is some set A of reals such that there is a very large convex subset of its sum set. So we have a large convex set inside a sum set. And this, how large? Well, B, size of B, this convex set's as big as possible. B bigger than A squared. Now, this feels like it's telling us that there's additive structure inside a convex set. The B, we have this, so it's a bit of a different kind of additive structure, but B here, it's efficiently contained in a sum set. So you can sort of just add a few more things and it becomes a sum set, but it's also convex, and sum sets should have lots of additive structure. So that's kind of, that's a result which is in a similar direction to the one I'm describing here. And what made us think that this could really help us was we just sort of imagined that there was a stronger version of this known and derived something from it. So here's Here's a second version of their statement, and I'd like to emphasize that what I'm writing down here is kind of a lie. They didn't prove this, so I don't want to misrepresent the truth here. This isn't really a theorem. I should have put some quotation marks here. It's more like, imagine this was true. It's a statement which is morally similar to the one above. We just strengthen it a little bit in a convenient way for our purposes. So I'm going to change, the main thing is that instead of B being a dense subset, B is actually just going to be equal to the whole thing. And I've just made another small change, and really just for technical convenience, I changed this plus to a minus. And we might think, well, plus and minus, it's the same thing, additive structure in both cases. So morally, it doesn't change much. So I made a couple of changes to the theorem, a couple of sort of wouldn't it be nice changes. And if we had this version of the statement, let's see how it helps us. So now we get, with this hypothetical set B, we get lots of solutions to this equation B1 plus B2 equals B3, which is almost like the 3AP equation, just without the 2. And that's just because of these trivial things down here, A1 minus A2 plus A2 minus A3. These A2s cancel each other, and we're left with A1 minus A3. This isn't a solution of this form. And we can do this for any of these triples, A1, A2, A3. And that means we have many solutions to this additive equation, which is almost like the 3AP equation. And many here is about b to the 3 over 2, which is matching the exponent from the theorem that we proved. So this doesn't prove our theorem because there were like 3 lies in here, but the lies are kind of small ones, and it gave us the idea that we could do this. And then once we had this idea, I think we figured out basically the construction within, I don't know, within a few days. So this was quite a key jumping off point for us. A very nice paper. So next, I'm going to try and describe in a bit more detail how our construction really goes. And so the idea for this construction is to, we define this 2 sort of parameter. I guess this is a function of 2 variables, B, L, K. What have we got here? So it looks a bit messy. Let's try and understand all of the parts of this. So yeah, there's some quadratic factor here, which is going to make this convex in K. K we're thinking of here as some variables, integer variables ranging from 1 to n. And L we're thinking also as an integer variable. N we're thinking is just some large number that's going to be sort of the size of the set that we eventually construct. There's a couple of other things here, and these alphas and epsilons are not very important unless you really want to get into the details. They really need to be there, but they are small, very small constants which serve some purpose. Which, let's see, maybe I can explain a bit more as we go on. So essentially, what our set B is going to look like is, our set A is going. We first of all construct B, which is all of these BLKs in this range. So we have about n squared elements of B. And what we're going to do is sort of carefully build a subset out of this B, which is going to be convex and with the additive structure. So in this next slide, I'm going to try to explain why this expression looks like a good candidate for something convex with additive structure. So think about how the 2 variables are sort of interacting here. If we fix K and vary L, what's happening? So K is now if we think about K as a constant and vary L, this is an arithmetic progression because the n's also constant, epsilon's constant. So all that's going to change is as this L increases, this is an arithmetic progression. So there we see that this B has some kind of additive structure. It has these large progressions inside it, progressions of length n in a set of length n of size n squared. So that seems like it might be useful. On the other hand, if we switch the variables around and fix L and vary K, then what we have are these kind of convex blocks. So I'm going to give some notation here. B sub L. This is the set we get just by fixing L and ranging over K here. And what do we have then? Well, yeah, what do we have here? We have this this linear factor K, as K varies, and then we've got this factor of this term which is quadratic in K. That's going to make this a convex set. This BL on its own. These individual blocks are convex. But because this alpha is chosen to be very small, it's not very convex. So if you kind of look at it, if you were to plot this with a computer and look at the picture, it looks like an arithmetic progression. Because this K is kind of the dominant term, even though there's a higher power K squared appearing, because the constant's sort of overwhelming it. So it is convex, but it's very slightly convex. So it looks just like an arithmetic progression if you don't look very closely. So then the idea is that we could take these very slightly convex sets, these blocks, and if we could kind of stick them together smartly, we would have a convex set with lots of arithmetic progressions. And basically what we do is that. So yeah, so B has this convexity, and these blocks are barely convex. So I say here that to the naked eye, they look like arithmetic progressions. And actually, this was also a similar. All of these ideas are quite close to the Roche-Newton construction. They also had something like a very slightly convex set in their result. Okay, so here, new slide, and I'm just reminding us the definition of this BL, these fixing L and varying K sets, these blocks, I call them. So the numbers are all set up in such a way that we get a structure a bit like this one I'm about to show here in this picture, that the way that these blocks overlap is something like this. So we can, if we're just being a bit sloppy, we can think about each block, BI, it's an arithmetic progression, almost, not quite, of diameter about 3/2. And we have n elements in there. And the next one starts, and the next block starts 1 to the right and has the same diameter. So you get this kind of overlapping parts here, which are shaded in red. And then these kind of blue parts here, which are unique to the block that they're in. So this blue sort of middle third, approximately, belongs exclusively to that block that it's in. It doesn't have to share with the next one. So now, if you remember that these arithmetic progressions are actually convex sets, the idea is that we kind of glue these together. We move along B1, and then somewhere in this shaded red region, we'd find a way to pass to the next block in such a way that we keep the union convex. So this passing has to be done with some care. And then we'd move along here and do the same thing now in the next red block, pass down from B2 to B3. And if we could do this, we'd know that these blue bits in the middle are guaranteed to be in this union, because then we're going to hit them every time because of the way these intervals overlap with each other. And then when we think more about what's going on in this blue bit here, well, these are the sort of middle chunk of BI. These all have K, the K parameter, somewhere approximately in the middle third of this range. So then we could sort of think about fixing K somewhere in this middle third, and we move down the blocks, sort of move straight down. That's where we see the long progressions. So the long progressions are coming from sort of fixing a point in this middle third and moving sort of vertically down. So that's pretty much the proof. Of course, like, you have to do this with real numbers, and there's some careful parameterization that needs to be done, some careful optimization that needs to be done. But that's pretty much the idea. There's one more sort of step in this idea, which is how can we pass? Like, how can we really get from this block to this block and keep the convex structure? And this is where this one of these small factors becomes important. So this epsilon factor in the definition, we didn't talk about it yet. It was there. It serves this purpose. Let's go back to this epsilon factor. It serves the purpose of making the next block a little bit more spaced out than the previous one. So it means that I've drawn them here that they all look the same, but because of this epsilon factor, this bi down here, this region is a little bit more spread out than the bi minus 1 above. And what that allows, if we think now we put them back on the same number line, think about the blue elements here are BL plus 1 and the red ones are BL. Now, because of the earlier block, the red ones are a little bit more densely packed, and I've exaggerated it for this picture because they're really almost the same. But eventually, somewhere, we should have 2 red dots in a row. That should happen as long as there's enough of a difference between the densities. So we get 2 red dots in a row, and then we can use that to pass from the red to the blue. So here's a picture of how we do that. You go along the reds, you follow the red dots, and then when you get this structure here with the 2 red dots in a row, that's when you pass to the blue. This is going to guarantee that you stay convex in the union. This was another nice idea from this Roche-Newton paper, so we really owe them a lot. So yeah, as long as you have this ABBA pattern, A, B, B, A, blue, red, red, blue, you can pass from one block to the next. I feel like I have an opportunity to express my love for the band ABBA in this paper, and maybe secretly insert some of their song titles into the text somewhere. That's the last task before we submit. Okay, so yeah, actually that's pretty much it. So I mean, if I talked more, then it just gets too technical and no one wants to hear that. So I guess that's like enough detail of this construction, but it's kind of a simple idea and it's not very technical to do it properly. Now I've got a few minutes left. Got quite sparse with the slides here. So I just want to finish in the last few minutes to mention one other problem that we considered in this talk. Sorry, in this paper, which is about SID-on sets. This is an important notion in additive combinatorics. So a SID-on set is a set with no solutions to this equation except for the trivial ones. So x1 plus x2 equals x3 plus x4 can only happen if the left-hand side elements are the same as the right-hand side elements. So we think of this as a very sort of unstructured set. It's got no additive patterns at all, except for the trivial ones. And if we have a set A, we could think about what's the size of its largest SID-on subset. You could think about this maybe as another measure of additive structure. So like if A is very structured, then you might have to remove a lot of elements to remove all of the solutions. If A is very unstructured, maybe A is already a SID-on set, for example, it's very unstructured, then S of A would just be the size of A. So if this quantity is very big, it means that the set's not very structured under this measure. If it's small, it suggests there's some structure in there. Kind of robustness of these solutions, I guess, is what we're measuring here. So yeah, here's an example. You take this very structured set, the first n integers. This has, the largest SID-on set has size about square root of n. Actually, it's a really big open problem in additive combinatorics to determine more precisely what this value should be, and the key, like the big question is, what's the error term? What's the second order term on this? So root n plus what? But I'm not really going to talk about that today. I'm happy to sort of just think about the main order being there, root n. So this is really nice and very general result of Komlosh, Shulyok, and Semerady, which says actually much more than I'm telling you about here. But in particular, it implies that this basically this interval minimizes this quantity. So, and that's kind of feels right. I think it's a very, very structured example, and there isn't one with more structure. So every set, no matter what it is, you can find a large stood-on subset of size about root a. Yeah, and the proof there is like a sort of, they somehow project this generic set down to be densely packed in the integers. It's kind of pretty clever and a bit mysterious, I think. So yeah, you can always get root a, but the question again is, can you do better with this convex assumption? So we think that convex sets aren't too structured, so maybe we think we could do better than the Komlosh-Shulyok-Semerady theorem with this assumption. And yes, one of the things in this paper we say is that yes, we can do a bit better. And this is, I suppose, like a fairly simple observation, really, in the end, using some sort of Alan Spencer chapter 2 probabilistic methods. So day 2 of your probabilistic methods course, you would learn how to do this as an exercise, I guess. If you were given some clues, maybe. So yeah, we use an elementary probabilistic argument and some bound on the energy. Actually, we arrived at this 3-term arithmetic progressions question as a consequence of trying to solve this one, because we needed a non-trivial bound for this 3 APs, and we kind of got a bit hooked on that problem. It became our main problem. Okay, so that's you can do a bit better with the condition that is convex. Oh, I haven't explained what this notation is. I think I've probably used it a few times. Sorry, I should have said this about 40 minutes ago. It's I'm subsuming here constants, but also log factors. So it's like so what it really is S of A is greater than a constant times a to the 1/2 plus 1 over 75 divided by log of A to some power. In our paper, we also give a construction which shows that the best you could hope for is the exponent 2/3. So again, it's sort of a set which is convex with some additive structure. And it's a very similar idea to what we've seen already. Let's check the chat in case there was anything important. I'll come back to that, okay. So very similar construction. Again, it's basically the Rouget-Zalesov construction again. So let's see. How do we make this convex set with this sort of, yeah, just to maybe reiterate what the statement says. It's saying that you have this convex set, and if you want to remove all of the additive solutions to the energy equation, you have to remove quite a lot of elements. The solutions are kind of robust. So I'm actually going to just finish now with a proof of a slightly weaker result, which you can get directly from Rouget-Zalesov construction. And here it is. So you've got this construction of this convex set with so tightly packed into a sum set. That's exactly what their statement says. And we can visualize this set as the edge set of a bipartite graph on A cross A. So here's a picture. We make a copy of A here, another copy of A, and so for every, sorry, I've stepped a step ahead. Sorry. So yeah, sorry. Let me go back a step. So we consider B as the edges of a bipartite graph, yeah, that's what we start off with. So every A1 and if say A1 and B1 is an element of B, then we draw the edge between them. And then suppose that there is a large Sidon subset inside this B. So that means a large set of edges, S, in this graph. Large means bigger than about b to the 3/4. Yeah, so there's weaker exponent 3/4 here. And the contradiction is going to be because this set S is quite dense, we have some graph theory which tells us that this set, these edges, with so many edges in a bipartite graph, we have the Roche-Newton theorem telling us that there must be a cycle of length 4. So, and a cycle of length 4 in this particular graph has to look like this. It goes from A1 to B1. So we've got A1 plus B1, B1 plus A2, A2 plus B2, B2 plus A1. And these things all have to be in the set S. But then we can use them to make a sort of trivial solution here. Well, it's a non-trivial solution, but it looks kind of trivial because we basically we swap some of the elements around. And according to the definition of Sidon, this is a non-trivial solution. So A1 plus B1 equals A2 plus B2, and then we kind of permute them, I guess, on the other side. Obviously, this equality is true, but this is also, these are all in our set S. So it can't be Sidon, and that's the contradiction. And what we did to get this 2/3, which I wrote down in the previous slide, is we just did an unbalanced form of this construction. So this argument works a bit better if you have a set A with size n, a set B with size n squared, and I'm sorry, maybe I should say a set A1 with size n, a set A2 with size n squared, and this B having size about n cubed. You can do that by modifying basically the numbers in the Roche-Newton paper, and then with this unbalanced form of the Roche-Newton theorem, things work out a bit nicer, and you get this Sidon exponent of 2/3. But of course, the question is, what's the right answer? We have a non-trivial lower bound, we have a sort of fairly non-trivial upper bound. There's still a big gap there. I might speculate that the right answer should be closer to this 2/3. It's interesting, though, that any improvement to this 2/3 would imply a refutation of this energy conjecture, which I suggested as false. And so we're right on the border for disproving the energy conjecture. And similarly, I mentioned this kind of main result. I'll go back to the main result. What was it? It's way back. Way back. Okay. This many 3APs result. If we improve this to plus epsilon, we also refute the energy conjecture. So we're right on the edge of disproving this energy conjecture, but actually, I think I don't think we can do it with these theorems because I suspect they're both optimal. So, but this is quite a lot of speculation going on here, so I should stop talking before I say something that I don't believe. Thank you for listening, and I'm happy to answer any questions.